So we're very happy to have Mauro di Nasso from PISA here to talk about non-standard natural numbers in arithmetic, Ramsey theory, and topological dynamics. Very excited to have you. So go ahead, Mauro.
So first of all, let me thank you for the invitation. I really love to talk about this topic. So I decided not to go much into technical details. I will do just about a couple of results, but mostly I would like to present this topic and this idea of mixing non-standard natural numbers, ultrafilters, and this kind of tools in Ramsey theory. And also I will mention briefly some connection with topological dynamics. That is also something I'm getting interested in. So let's, okay. So this is the plan of the talk. I will start with some overview, very quick, very easy, I think.
Right,
about
Mauro, we don't see it.
Yeah, I think we're still on your title slide.
What happened here? Summary, and I was saying that the first part will be about a short overview of what arithmetic Ramsey theory is. Then I will talk about about non-standard natural numbers, ultrafilter types, and how they mix, how these notions are mixed, and then give a short proof of Hyman's theorem by using this non-standard setting. I will talk about independent pairs, which give rise to these idempotent points, and also, well, give a proof of Ramsey theorem. And then, as I said, I will mention also connections with topological dynamics that I will perform in these hypernatural numbers. And then I will present some recent results that I found about monochromatic patterns in the integers by using some unusual semigroups on the integers. Okay, so let me start. So what is arithmetic Ramsey theory? Is, of course, a topic in Ramsey theory, and which focuses on configurations in the integers. Of course, one could also consider other rings or semi-rings, but let's focus on the integers to make it simple. And when we talk about patterns or configurations, a family of patterns is simply a family of subsets of the natural numbers. And here are three relevant examples. The so-called sure triples means sets of the form A, B, A plus B, multiplicative sharp triples, sure triples, and arithmetic progressions, this kind of combinatorial configuration. Now, a typical problem in this arithmetic Ramsey theory is the following. You are given a finite coloring of the natural numbers, meaning a finite partition. And the problem is, can I always find a monochromatic pattern from the given family? Meaning, can I always find a color and a set in the family so that the set is included in one of these pieces of the partition? If this is the case for any finite coloring, one says that the family is partition regular. Now, there are many examples of partition regular families. So the easiest of them all is, say, the family of infinite sets. Of course, given a finite coloring of the natural numbers, one of the colors will be infinite. Or the set of positive asymptotic density. But there are also more specific configurations that are considered in arithmetic Ramsey theory. And historically, this is the one that you are seeing here is probably the first that was proved to be partition regular and it was used by Hilbert in proving his irreducibility theorem. So you take all possible expressions of the form A plus the sum over F of bi for I in F, where F is a subset of 1 to n, and this was called the n-dimensional affine cube. But now let's just go back to the very simple configurations. A very famous one, a very celebrated one, is the configuration that was considered by Schur. And in fact, it was considered when he was trying to prove Fermat's last theorem. And indeed, he was able to prove that Fermat's last theorem is false in some sense in the finite fields Z PZ for sufficiently large primes. And the basic combinatorial property that he used, and by the way, there is a really nice proof of that property starting from this combinatorial property. The property is that in any finite coloring of the natural numbers, you always find a monochromatic triple of the form A, B, A plus B. Now, in his theorem, he used the finite version of that, but by compactness arguments, as they used to say in combinatorics, which is nothing else than the compactness theorem in logic, after all. And he proved the finite versions, but it is easily seen that the finite version and the infinite versions are equivalent. And we will focus on infinite versions because in some sense they are easier to prove. And Ramsey theory, of course, comes after Ramsey theorem. So the results that are presented before were historically before the proof of Ramsey theorem. So you probably all know the theorem of Ramsey. If you have an infinite set, you give a finite coloring of the K sets, meaning the subsets of X of cardinality K, and you always can find a homogeneous set, an infinite homogeneous set, which means a set with the property that all subsets of K elements taken from this H belongs to the same piece of the partition. This is Ramsey theorem. Now, for instance, nowadays the proof of Schur theorem is an almost trivial exercise, an easy application of Ramsey theorem. So in this case, you take all pairs of the natural numbers and you give a pair the same color as the distance between the two numbers. And you find by Ramsey theorem an infinite homogeneous set, which is much, much more than we need to prove Schur theorem. You just take three elements in this homogeneous set, and you have the distances y minus x, z minus y, and z minus x form a Schur triple, which is therefore monochromatic. Another cornerstone of combinatorics, arithmetic Ramsey theory, is van der Verden theorem, saying that in every finite coloring of the natural numbers, one can find arbitrarily long monochromatic arithmetic progressions. The proof is not so simple, but can be done by elementary methods in combinatorics. Now, let me just mention this fact that many of these Ramsey properties have a density version. In other words, for instance, the density version of van der Verden theorem is Zemeredi theorem. And that is much, much harder to prove. And it states that if you have a set of positive asymptotic density, meaning that the relative density of the set when over the interval 1 to n these relative densities has a positive supremum, upper limit. So if the set is large in this sense, as positive upper asymptotic density, then you can always find in the set arbitrarily large arithmetic progressions. Of course, in any finite coloring, you have at least one color which has positive asymptotic density. So van der Verden is just a corollary. But this kind of property are considered to be really interesting. For instance, it's the famous result by Tao and Green saying that one can find arbitrarily large arithmetic progressions in the primes. Now, it is probably one of the most relevant open problems in this area. If any other set having the same, the same largeness as the prime, meaning asymptotic going to n over log n, if any set of this form contains arbitrarily long arithmetic progressions, because the point is there some specific property of the primes that produce arbitrarily long arithmetic progression, or is just a matter of how large the set is?
Mauro,
so this is still open.
Mauro, sorry, can you say a little bit more about it, about this any other? Okay, if you remove one prime, it still has the property. So what's the meaning of other here?
For instance, if you take a sequence of natural numbers with the property that the reciprocals are diverging, you can find arbitrarily large arithmetic progressions in that sequence. So this is the usual formulation of this conjecture.
Right.
So it's an asymptotic notion of largeness.
Thank you.
Of course, the density of the prime, the asymptotic density of the prime is 0, but it's close to something, I mean, but not so small in some sense. So it is still a large enough set. And question is if for those kind of sets, one can prove similar results. I also would like to talk about density properties, but in this talk, I will focus only on the Ramsey theory side. So let me proceed a little bit. There is also a notion of partition regularity for equations. So what does it mean that a given equation is partition regular? It means that in any finite coloring, you can find elements of the same color which are a solution to that equation. So for instance, Schur theorem is just a partition regularity of the equation x plus x1 plus x2 minus x3 equals 0. Because in any finite coloring, you find x1, x2, x3 satisfying that relation. And for instance, having monochromatic arithmetic progressions of length 3 is the same as to say that the equation x1 minus 2x2 plus x3 equals 0 is partition regular. Now, these kind of problems are nowadays well known because there is a classic result of Rado. So you see the results are from the 1930s, so they are old results. And he was able to find a really nice condition. So if you have a Diophantine equation, you can immediately say if it is partition regular or not. The property, the characterizing property is the one that is written there, meaning that a partial sum of the coefficients must equal 0. And you see that this is indeed the case for the equation for sure theorem and for 3 terms arithmetic progressions. But not all equations are, of course, partition regular. Now, let me mention that recently there was a study of the nonlinear case. And in that case, things get much, much more complicated. And it is still open, the problem of finding some easy, effective condition in the style of Rado about nonlinear polynomial equations. For instance, I don't know, it could be also that it's not a decidable problem in some sense. It's not clear, because if you talk about all possible nonlinear equation, could be a problem in a way similar to the problem of establishing if the given equation has an integer solution or not, in the style of Hilbert problem. So let me, for instance, mention that there are still open problems that are really easy to state, and we don't know much. A famous one is the Pythagorean equation. So we don't know if in any finite partition of the natural number, one always finds a Pythagorean triples. Okay. And another one that I will mention later in the talk is the partition regularity of the configuration that combine additive and multiplicative sure triples. So we don't know if in any finite coloring one can find A, B, A plus B, A times B of the same color. This is not known yet.
Hi, I'm sorry. Could you just repeat the definition of partition regularity? There's many quantifiers in it that slipped my.
I will go back to this.
Here, yeah.
In any finite coloring, you have to find one color that contains elements which are a solution to the given equation.
Of the natural numbers, and find monochromatic. All right, okay.
So for instance, about Pythagorean equation, you need, if you have three colors, one color must contain A, B, and C in such a way that they form a Pythagorean triple. And same thing with these kind of patterns. You need to find A, B, A plus B, A times B in the same color. Now, let me just mention several partial results about the Pythagorean triples that seems to suggest that the equation is partition regular, but this is not a theorem yet. And you can see, we can start from sure theorem. Then we have variations like x squared plus y equals z. It is partition regular. It is a result by Sarkozy and Fürstenberg. X plus y equals z squared is not partition regular. And we will see a proof of that by non-standard methods that I would like to present just to give you an idea of the non-standard methods I'm going to introduce. And you see x plus y equals z squared is partition regular for two colorings. So it may be the case that some equations look partition regular for two colorings, but not in general for finite colorings. And for instance, there was this famous result in 2016, the last one that is mentioned here, where they proved with a computer-assisted huge proof that for two colorings, one has the partition regularity of the Pythagorean equation. Now, there are two problems about this proof. First, problem is that, of course, one person cannot go through the details of this proof because it's enormous. And in fact, it was considered, it was published in Nature, I think, or in some of these journals as the largest proof ever. But it's only for two colorings in any case. So it is still open whether the Pythagorean equation is a partition regular equation. So you see all kind of variations are known, but the Pythagorean equation is still a mystery. And let me mention, and I will mention this later in the talk, that Schur theorem has several possible generalizations. For instance, one could ask for 3 elements with the property that the sums, all possible sums, are monochromatic. And this is true. It was proved in the 70s by Folkman. For any k, one can find k many elements with the property that all possible sums from these elements are monochromatic. And finally, the celebrated Hyman's theorem, which is a real jump with respect to the previous theorems, because he proved that one actually has an infinite set, an infinite sequence with the property that all finite sums taken from that infinite set are monochromatic. And we will also prove this by non-standard methods, just to let you see how this idea of taking non-standard numbers can be used. So now I just presented a few of the basic results in this area, and we have to understand what does all this have to do with non-standard natural numbers. Now, the idea is that non-standard natural numbers can play the role of ultrafilters on the natural numbers, and it is known that ultrafilters play an important role in Ramsey theory. I will discuss this. And also, we will see that non-standard natural numbers have a natural compact topology, and one can consider topological dynamics on the happier natural numbers. And this will also produce nice and interesting results about combinatorial properties. So let me remind you what an ultrafilter is. Here is the definition of filter. It simply is a family of subsets which is closed under finite intersections and under supersets. So in some sense, it is a notion of, we could say, of relevant property. So a set is relevant if it belongs to some filter. A filter gives a notion of relevant. So probably the most important one is the filter of cofinite set. So for instance, when considering limits in the classical sense, the relevant set are the cofinite set. So for every epsilon, we want a cofinite set of indexes so that the sequence will be epsilon close to the limit. Now, an ultrafilter is just a maximal filter. And equivalently, the property that one has is that for any subset, either the subset or the complement belong to the ultrafilter. And this is the same as to have the partition regularity property. So we already see how this object ultrafilter is connected with Ramsey theory. The proof of the existence of non-principal ultrafilters requires the axiom of choice. So except the trivial cases of principal ultrafilters, so one take a number and then take the family of all subsets containing that number, that is a trivial example of ultrafilter, but the other ones, the non-principal ones, require some form of choice. So the sets in an ultrafilter are not the big ones in some sense, because any set you have, you split it in two parts, only one of the two belong to the filter, to the ultrafilter. So I don't think the intuition of sets in an ultrafilter to be large is the right one. One could say that they are, in some sense, a notion of positive property, in the sense that the negation will be, the negation of a negative property is positive. But I mean, this is just to give some intuition. Now, it is easily seen that partition regularity and ultrafilters are strictly connected, because a family is partition regular if and only if you have an ultrafilter that is made of sets belonging to, well, belonging, that contains as subsets elements of P. So for instance, the theorem of Schur, and saying that the Schur triples are partition regular, is the same as to say that there exists an ultrafilter on the natural numbers with the property that that is a witness, in the sense that every set inside the ultrafilter includes a Schur triple. And since one direction is trivial, in any finite partition, exactly one of the color must belong to the ultrafilter, because this is the property of ultrafilter. The other direction is easy as well. It takes 3 or 4 lines of proof, but it's really elementary. So I mentioned ultrafilter. Now let me mention what we mean by non-standard natural numbers. Of course, I cannot introduce non-standard analysis from scratch. I think all of you know what it is, but let me just mention that nowadays we are talking more about non-standard methods rather than non-standard analysis, because it started as with applications in calculus and analysis, but then developed in application to topology or to functional analysis and many other topics, including now Ramsey Theory and combinatorics. So non-standard methods. So let me just mention the basic ideas of non-standard analysis. Anytime you have an object that you are studying, one can consider the hyperextension of that object. So if you are interested in the natural numbers, you will have a hyperextension of the natural numbers. And of course, there is a transfer principle, which is an elementary embedding property, which means that any elementary property, meaning first order property, holds for object A1, AN, if and only if it holds for the corresponding extensions. So this map star is a strong version of an elementary embedding. So to be precise, for instance, the hyperextension, say, star R of the real numbers is an elementary extension in the strong sense that it is an elementary extension with respect to the complete language. It's what is called the complete elementary extension. So in non-standard analysis, you don't have countable languages. You have an extremely rich language where you have one symbol for any possible constant, function, and relation. So if you're starting with the natural numbers, any subset of the natural number will be definable. It will have, say, formally a constant corresponding to each of the subsets. And same thing with relations and constants. In any case, just think of this star n as a non-standard model, say, of Peano arithmetics, but with much more, because you have a much richer language, and so you can perform many more things. But the structure is the same, of course. You have the finite numbers, and then you have the infinite numbers. The order structure is something like this. Now, the connection between hypernatural numbers and ultrafilters is a straightforward one and was considered already in the old days of non-standard analysis. So you take any element. We are interested in the natural numbers, but of course, these kind of things could be considered in more generality, but you take any non-standard number and you take, say, all properties that are satisfied by this number, all subset of the natural numbers, so that this number C satisfy the non-standard extension of the corresponding property. So in a precise sense, this ultrafilter is the one type of the element C in the non-standard model. The point is that since every subset is definable, for any subset, you can decide if the subset belongs to the ultrafilter or not. So you have the property of ultrafilters. And if you have the model, the non-standard model, to be sufficiently saturated, you have that any possible ultrafilter corresponds to some element. So every ultrafilter, in some sense, becomes a principal ultrafilter in the sense that it is generated by some ideal, infinite, non-standard natural number. Yeah. If you have questions, please feel free to ask. Now, okay, I didn't mention this, but we will always assume the hypernatural numbers to be saturated enough so that we have all possible ultrafilters. But in this case, it can be proved that you have plenty of elements generating the same ultrafilters. So we have a non-trivial equivalence relation. And we can say that two elements are equivalent, U equivalent in the sense that ultrafilter equivalent, if they generate the same ultrafilter. This is the same as to say that there is no way of distinguishing the two elements by means of standard properties. So for instance, you take any property you want of the natural numbers, and either both of them satisfy the property or both of them do not satisfy. In this case, you say that the two elements are equivalent. And this, of course, corresponds to the property of having the same one type, or to say that the two elements are indiscernible. Now, what is the use of this notion? First of all, let me just mention a few very easy stated properties of this equivalence. If you have two elements which are equivalent and they are different, then they have to be at infinite distance one from the other. You cannot have a number and a number plus 10 which are equivalent. This is easily seen. One can immediately find a property satisfied by one but not by the other. And then we have the properties 2 and 3, which are very useful in practice. The first one says that if two elements are equivalent, then if I take any function, standard function from the natural numbers to the natural numbers, and in non-standard analysis, every function is part of our language, then the images of these two elements will still be equivalent. And there is also the third property, which is non-trivial. I think, because it corresponds to the property of ultrafilter, which is a basic one. Anyone studying ultrafilters knows that this property is very basic, but still is not trivially proved. It takes some little combinatorics to prove that property. And the corresponding
Mauro, sorry.
standard setting is property 3.
A question. So in just the language of arithmetic, that would be Ehrenfeucht's theorem. So is the
what is this theorem? Say it again.
Well, Ehrenfeucht. If f is a definable function, you have just the language of arithmetic, not the full language. So this is Ehrenfeucht's theorem, which has combinatorial proof of sorts. And I just wonder if the ultrafilter proof that you had in mind is that it's somewhat combinatorial. Is it really the same in nature? Do you know?
I don't know. I know, of course, the proof about ultrafilters, but it
maybe
takes 3 colorings of elements.
Right. So it seems to have similar flavor, and Vika probably knows the answer. Vika, do you? Oh, I don't know if Vika is there. And
the meaning of this.
Vika wrote a paper on this. So
can you say again what you want to know, Roman? Because I was
Mauro mentioned that this item 3 is somewhat, it's a basic result about ultrafilters, and it has a combinatorial proof. And I said, in the case of just language of arithmetic, this is Ehrenfeucht's lemma.
Right.
And I just wondered if there is some correspondence between the proofs, because there are combinatorial proofs. There is original Ehrenfeucht's proof that has some element of combinatorics, but then you came up with some proofs. Jim has a nice proof using coloring, 3 colorings of definable graphs. So I just wondered if there is some correspondence.
It looks like the ultrafilter proof, because in ultrafilters you use a 3 coloring.
That's exactly what Jim used. But then Vika also had some variants of the proof. Vika and Joel Hamkins, if I remember correctly.
Roman, this has been ages ago, but what I'm remembering is...
Well, I would say a couple of years ago.
We rather had counter examples for set theory.
That's
and not proofs for the and not any alternative proofs.
Well, no, but your proofs were sort of very sort of anyways, but it's a digression.
Now I have to go and look it up. Okay.
I'm curious. I will check this.
So Jim's proof is in our book, somewhere in the exercises, and it's a very nice short proof that probably you can come up with yourself. It uses 3 colorings.
It's possible it's the same, but I will have to the same. I mean, the idea should be really similar, I think. In any case, I want to double check this. But I was saying this is not entirely trivial and can be used in practice, and I will show you in what sense in the next slides. So this U equivalence is useful in partition regularity problems, starting from this non-standard characterization. So if you have an equation saying that the equation is partition regular on the natural number is exactly the same as to say that one can find equivalent hypernatural numbers that are a solution to the equation. So for instance, Schur theorem says that there exist equivalent non-standard numbers xi and zeta so that they are also equivalent to c plus z. So instead of saying every time in any finite partition I can find something, you go straight and say you have equivalent non-standard numbers satisfying something. That isn't exactly equivalent. So let me show you how one can use this. This is really useful in proving that certain equations are not partition regular. So this is one example. And let me tell you that this is much, much shorter proof than the original one. So one of the results, the initial results about nonlinear equation is this one that was finding 2012, the equation x plus y equals z squared is not partition regular, except for the trivial case when x, y, and z are all equal to 2. Okay, how one can prove by non-standard methods this one? I think this is a very simple example, but already says that this could be a nice way to approach this kind of problems. Now we proceed by contradiction. If it is partition regular, then you can find alpha, beta, and gamma, which are equivalent and satisfy the equation. Now take the function that for a given n, find the greatest exponent of 2, which is smaller or equal than n. Okay, this is a perfectly nice function. And of course, even the non-standard number alpha will have such an exponent. Let's call it a. Of course, a is infinite. Okay, because if a would be finite, otherwise alpha would be finite as well. And if we have a finite number which is equivalent to another number, then it has to be equal to that number. So for instance, there is no number which is equivalent to 17 except 17 itself, because you have an actual property that you can write down to describe, to characterize 17, okay? So the case when a is finite can only be the case when alpha, beta, and gamma are equal to 2. And that's the case that we don't want to consider. So we can assume that alpha is infinite. Now, let us assume without loss of generality that alpha is greater or equal than beta. And then you have this very simple line of inequalities. So of course, by definition, 2 to the a is less or equal than alpha. Alpha is smaller than alpha plus beta, which is equal to gamma square. Of course, gamma square is less or equal than to alpha because we are assuming alpha to be larger or equal than beta. Since alpha is less than 2 to the a plus 1, we have the equality with 2 to the a plus 2. Then we divide, we take the square roots. So we have 2 to the exponent a divided by 2 is less than gamma, is less than 2 to the power a divided by 2 plus 1. Okay, so in this case, the exponent of gamma can be either the integer part of a divided by 2 or a divided by 2 integer part plus 1. Now, a was the value of alpha under the function f, but since alpha and gamma are equivalent, also f of alpha and f of gamma are equivalent. So we have that either a is equivalent to the integer part of a divided by 2 or to the integer part of a divided by 2 plus 1. Now we are using the property number 3. If the function of something is equivalent to that something, the two elements must be equal. Is the property 3. That one. So the conclusion is that either a is the same as the integer part of a divided by 2, and this cannot be because a is positive, or the other equality, integer part of a divided by 2 plus 1. But then it must be a equal 1 or a equal 2, which is against the assumption that a was infinite. And this is the proof. In standard terms, of course, you could translate back this by considering a coloring, and you take one color for each of the properties that you considered in this proof. As an exercise, you can try to write down the actual finite covering, giving you a counterexample to the partition regularity of the equation. But it takes some work, and I think that in this way, everything is really transparent. I have another proof of this kind, but I'm afraid I will not have time to say everything. I mean, probably I will just stop at half of the talk, but I think this is nice. For instance, one can prove that x squared plus y squared equals z is not partition regular by using similar ideas. Again, you assume by contradiction that you have equivalent numbers satisfying the equation. You factor the number by considering the prime number 2. Now they are equivalent, so they are A, alpha, and gamma. They are all even numbers or they are all odd, but they cannot be all of 3 odd, otherwise they will not satisfy the equation. So they must be even, so the exponent are positive. And I'm not going through this, but I mean, it's really simple. They are really simple arithmetic properties that one uses. Nothing fancy after all. So you just distinguish the 2 cases and you get contradictions in both cases. And you are using at some point, again, the property 3. So you see that at some point you have the 2a is equivalent to c, sorry, 2a is equivalent to a. And again, by that property 3, this would imply that 2a equals a, and you get the contradiction. And even in the case 2, you get a contradiction because you would have 2a plus 1 equivalent to a, which produce the equality 2a plus 1 equal a, which is again a contradiction. Okay. So let's go now to another fundamental ingredient, is the notion of independent pair. And I was told, I think, by Roman for the first time, who noticed that this notion is indeed a notion that is considered in model theory, is related to the notion of cohere. So in non-standard terms, one can state this property in a very simple form and say that a pair is independent, a pair of hypernatural numbers, if whenever the pair belongs to some set, to the extension of some set, then there must be some finite natural number n with the property that n beta belongs to the set, to the extension of the set. So whenever alpha beta belongs to star A, also n beta belongs to star A for some finite n. So if you translate this property into a set theoretic language, the generated ultrafilter is a tensor product of ultrafilters, which is a very basic operation one can do with ultrafilters, is defined there. It corresponds to a product of measures. If you say an ultrafilter has a 2-valued measure, finitely additive 2-valued measure, then it is precisely the product of measures. Now, by saturation, since independent pairs corresponds to this kind of ultrafilters, if there is saturation enough, all kind of ultrafilters are realized by elements, and so we will have plenty of such independent pairs. So no problem to have the existence of such pairs. Now let me give you a proof of Ramsey theorem by using independent pairs. And to make it simple, just consider the case of pairs. So you have a finite partition of the pairs of natural numbers. One can identify the pairs with the upper diagonal, in the sense with the ordered pairs nm, so that n is less than m. And so this is the proof. We pick an independent pair. Of course, the independent pair, one can easily show that an independent pair alpha beta, if alpha beta is an independent pair, then alpha is less than beta. So they belong to the upper diagonal. And if you have a finite partition of the diagonal, then of course the pair must belong to one of the colors. So now we simply have to prove that if an independent pair belongs to some star C, then there is this infinite homogeneous set. And the construction is there. It's just comes from the properties of independent pair. If alpha and beta, if the pair alpha beta belongs to star C, there must be some finite H1 so that H1 beta belongs to star C. Now, alpha and beta, they are equivalent because we are taking an independent pair where alpha and beta are equivalent. That was the hypothesis. So also H1 alpha belongs to star C. Then we take this set. And at this stage, we need the power of non-standard analysis, because this set is just a set of pairs. And in non-standard analysis, we could take any possible subset of the natural numbers or of pairs of natural numbers. We are not concerned with definability. Everything is definable here. So we are taking all pairs where the first component is larger than H1, and the pair belongs to C. The pair H1M belongs to C. Now, of course, the pair alpha beta satisfy that property, belongs to that set. So we have some finite H2 so that the pair H2 beta belongs to this, to the extension of this set. This means that we have H2 larger than H1, H1, H2 belongs to C, and the pair H2 beta belongs to star C. And since beta and alpha are equivalent, also H2 alpha belongs to star C. And we go on in this way. So I'm not going through details. You then consider the set gamma 2. And slowly, step by step, you produce elements H3, H4, and so forth, so that all pairs Hi, Hj with I less than j belongs to C. So you get the homogeneous set by a simple induction. Okay, let's go one step ahead. And we also have elements that we call idempotent because they will correspond to the so-called idempotent ultrafilters. So the property is this one. An element is idempotent if whenever this element belongs to star A, this looks strange, but let me explain this later. Then also this element Ni plus a finite element of A must belong to star A. It looks strange, but it means that you have, whenever you have an element satisfying a property, then you find a finite element satisfying the same property with the property that the previous element plus the finite one, the sum, satisfy again the property. So one could say that an element is idempotent if and only if there is an independent pair that satisfies sure property in the sense that alpha, beta, and alpha plus beta are equivalent, but the pair must be independent. Otherwise, you simply have, say, sure theorem. If you are able to take a pair which is also independent, then you will have much more. And in fact, this kind of elements will produce idempotent ultrafilters, or directly the proof of Hyman theorem. So I'm mentioning that an element is idempotent if and only if the generated ultrafilter is idempotent in the sense of this operation that is considered on ultrafilters. But if you don't want to think about ultrafilters,
Mauro, sorry,
yes.
Can you go back to the previous page, because I was still, so in the definition, can you clarify, the connection? Is there a connection in A and star A?
Well, star A is the interpretation of the, say, relation A in the non-standard model.
Right, but then you say if for every A. So I'm getting a little confused.
Yes. This element has the following property. If the element ni satisfy a property, so let me say, probably I wrote this in model theoretic terms. If ni satisfy the property of A, say that A is the set of.
Right, but you at the very beginning you already assumed that it is in A star.
Okay,
so maybe
this was a mistake.
All right, sorry. So okay, right.
An element ni
And right, if for every A, right. Okay.
Sorry. I'm not assuming this element belongs to star A.
Okay.
This was just a
typo.
A misleading typo. Sorry. Sorry. An element is idempotent is if whenever the element belongs to star A, then also the element plus a finite one also belonging to A belongs to star A. Okay. This is a remark. I mean, there is this pseudo sum operation between ultrafilters, which is not a commutative operation. Is defined in this way by taking shifts. And the idea that this sum corresponds to the sum of the generating elements is not correct. And in fact, one has the identity only for independent pairs. So these independent pairs are important in this context. They produced Hyman theorem, a Ramsey theorem, and in a somewhat similar way, they will produce a proof of Hyman's theorem. So this is what I was saying, that the notion of idempotent can be formalized in any, say, model of Peano arithmetic. So an element is idempotent if that property holds, meaning that if C satisfies the property phi, then there is some finite element satisfying phi, so that also C plus n satisfy phi. Now, since we have proofs about the existence of idempotent ultrafilters, and since we are assuming saturation, we will have elements which are idempotent. Now, my question is there a nice, direct, model theoretic proof of the existence of idempotent elements? That would be interesting, because these objects are central in this area of Ramsey theory. So any alternative proof would give important information. Okay, so let's go back to this Hyman theorem. It's a strong generalized version of sure theorem, where one has an infinite sequence of elements with the property that all possible finite sums belongs to the same piece of the partition. And the original proof was not easy. Hyman likes to make jokes about that. The ultrafilter proof is much simpler, but the idea of the ultrafilter proof can be isolated, and one can have this really short proof by using idempotent elements. And you see, you just use the definition. So you take the idempotent element, and since you have a finite partition, that element must belong to one of the pieces of the partition. So this, say, belongs to star C. Then all you have to say, to prove, is that inside the set C, you have the infinite sequence. And you proceed in a way that is somewhat similar to what we did to prove Ramsey theorem. So by definition of idempotent element, there must be an element x1 belonging to C with the property that Ni plus x1 belongs to star C. And now we proceed by induction. Suppose we already found n many elements of the sequence, so that all possible sums from those elements belong to C, and also the infinite element Ni plus each of these finite sums belongs to star C. So this is the hypothesis. Now we know by the hypothesis that this element Ni belongs to star C minus XF for every finite sum XF. And again, by using the property, the definition of idempotent element, we can find an element xn plus 1 which belongs to that intersection, with the property that also Ni plus xn plus 1 belongs to that intersection. If you translate back what it means to belong to those intersections, you get the desired property. So you will have that for any subset of 1 and n plus 1, all the finite sums xg and Ni plus xg belongs to the set. And that's a proof of Hyman. It's not a, I mean, I'm not hiding anything. This is the complete proof of Hyman's theorem by assuming this idempotent element. Okay, I think I'm late already. So I don't know what to do now. Let me just
Mauro, I have a suggestion. This is
Yes.
something that's happening over and over again at these seminars, that speakers come and then usually present about 1/3 of what they were planning to do, which I think is a good thing, because perhaps you will agree to come again and finish the talk slowly, sometime in January or February. How about that?
To me, it's fine. To me, it's fine, because of course, it's also nice to have questions and to.
Atar, is that okay?
I don't want to speed
Yeah,
up too much.
that
I mean,
sounds great. And I think that's a good place to stop with the. Do you want to introduce this to say something about what you might talk about next time, or do you want to just stop and take questions at this point?
okay, just let me present the next 2-3 slides just to introduce this, and then
Yeah, that's fine.
I will stop here. Okay. And then there is also the last part with the new results about monochromatic configurations. So this could be the topics of the next talk. So let me just introduce this topological dynamics. If you take the non-standard natural numbers, in non-standard analysis, it was considered a natural topology, the so-called standard topology. And the basic Clopen sets are the hyperextensions of the subsets of A. So this corresponds to the so-called logic topology model theory. Of course, that is defined on the set of types, but I mean, to us, elements are types in some sense. So the topology, the topology is really simple. You take all possible subsets of the natural numbers, you take the hyperextensions. Those hyperextensions will be a base of open sets, which are also closed. So you will have a disconnected zero-dimensional topological space, which of course is really close to the so-called Stone-Check compactification on ultrafilters. Sorry, the Stone-Check compactification on a discrete space can be seen as the space of ultrafilters with the family of basic open sets given by those families. The ultrafilters with the property that some given subset belong to the ultrafilter. Now this, okay, but I don't want to start another talk, but the point is, just let me say something here just to see. There is a strong connection between this topology and the space, the Stone-Check compactification. On the other hand, we have a compact topology, which is not Hausdorff, but still suitable for topological dynamics. We take the shift by one, that is a continuous function. And so we have a discrete topological dynamical system. And starting from here, we can find, again, nice combinatorial proofs by using basic notions in topological dynamics. Let me stop here because I'm sorry that
No need to apologize. So I think let's thank Mauro for a great talk. And if you'd like to, you can use your emojis to clap, or you can unmute and clap. So thank you.
Or both.
So let me display this commercial thing in case you are interested about applications of non-standard methods in Ramsey theory. This is a place where you can find several such applications.
Thank you. Let's open the floor for questions. There were, of course, several already, but we can continue. So are there any anyone, if you'd like to, feel free to just jump in.
Well, all right, to get things rolling, let me ask, where does, if anywhere, where does Alec Wilke's proof of Gromov's theorem on the growth of finite, words in finitely presented groups, polynomial growth and all that, which used non-standard analysis, non-standard models of Peano arithmetic in a way that, does that play a role in the history of these developments?
Well, I think, in non-standard analysis, we have this notion of hyperfinite set, which is extremely useful because it's sort of bridge between finite and infinite. And one can use that also, if I remember correctly, in some of the parts of that proof. Because this idea of non-standard things, for instance, if you have this, I should be more precise, but I mean, for instance, when one uses the so-called pseudo-finite groups of approximated sorry, I mean, I used to know about that proof. Now I need to check that proof again. What I remember is that this notion of hyperfinite set was used in a nice way, of course. And I think that many of the notion in that proof, or whenever you consider ultra products, the natural, to me, the natural framework where you could rephrase in a single language all those construction is non-standard analysis in these models. But you need more than just elements. Say more than just hypernatural numbers. You need to deal with subsets. So hyperfinite subsets. And then things are not so straight and so easy, but still I believe the language is the right one. But about your specific question, I mean, I need to.
Yeah, I just have a very short comment about it, which is, not about the proof and technicalities, but there was also another problem of Gromov. I think that Simon Thomas and Boban Veličković solved by using non-standard method. And I remember Simon giving a talk for us at CUNY, and he started by saying, what's really this methodology here when you have to deal with large and growing finite structures with some asymptotic behavior. Then if you want to use non-standard methods, then you just take your glasses off.
Alec presented that, but I think was one of the first presentations was actually at a meeting at Brooklyn College around 1981. That's why I'm fond of the theorem.
I had an unrelated question to this discussion if we've moved on. So, and when you were talking about these results about partition regularity of equations, specifically the negative results, you mentioned you can take the non-standard methods proof and you can translate that into a direct construction of coloring. And I was wondering if you know just how effective that translation is. So in particular, like the coloring you get, is it a computable coloring on the natural numbers, or is it more computationally complicated than that?
I never did it directly, but I think it's, I mean, when the proof, as the two proofs that I presented are in a way transparent, so you're using a small number of arithmetic properties for those proofs. And then you use that property 3 that I mentioned maybe a couple of times.
But you're using it these functions that are themselves very concrete and computable.
Yes, right? Yes, because property 3 for a given function correspond to a specific 3 coloring of the natural numbers. Because that is the 3 coloring that is used in the proof of that property. So you just accumulate a small number or a large number, it depends on the proof of the non-standard proof you have of properties. And then you produce, I don't know, it coloring in 20, 30 colors. But you see, if you want to start as a counterexample from a 30 of a coloring in 30 pieces of the natural numbers, well, it will take some work.
I don't want to do that.
Okay. On the other hand, in this way, you go directly to what you want to obtain in some sense. I believe that even the original proof was grounded on, of course, similar ideas, but it took much more technicalities to go through.
No, the non-standard message proof is very beautiful.
Things are more technical, but if one is used to this non-standard language, things are really more transparent. Because you immediately see the properties you are using.
No, I agree. The non-standard methods proof is very nice. So thank you.
Any other questions or remarks?
A quick question. It's these constructions. So I guess in the background, you do have ultrafilters and the axiom of choice.
Yes, at some point, yes.
Yeah, so are there any open questions whether or not some of these theorems require the axiom of choice in the end?
Well, I don't think these arithmetic properties that I presented today, I don't think they need the axiom of choice. But Hyman's theorem is, well, it doesn't take, I'm not sure. No, it doesn't take the axiom of choice. This was proved because it is a sort of properties that can be formalized in a way that one can apply the absoluteness lemma that says that if a properties of that syntactic form can be proved in V by using V equal L, so by using the axiom of choice and by using the continuum hypothesis also, then it is already a theorem of ZF.
Oh, very nice.
There is a simple absoluteness argument that you can use to say, for instance, that Hyman theorem, although we are using alpha filters to prove it, is a theorem of ZF.
Cool.
Now, to find explicitly a ZF proof, that's a different story. This was observed already many years ago. I can find a reference if you're interested.
Okay. All right. So let's thank Mauro again. Unless I'm missing a hand or anything, but let's thank Mauro again. That was great. I really enjoyed that. So thank you.
Thank you. And sorry for
let me
not
stop
organizing well the time, but
don't worry about it. Let me stop the recording here.